Hello, everyone. So, welcome to the series of lectures on the topic cardinality of sets, infinities, and diagonalization as part of the theory of computation course. So, I'm Arvind Vijayaraghavan. I'm an assistant professor of computer science at Northwestern University. My name is a little long, so you can call me Arvind. To tell you a little bit about my background, I grew up in this small coastal town called Pondicherry in southern India. This is a town where the fictional character of Life, I mean, in Life of Pi, well, Pai Patel, he hails from. I did my PhD at Princeton in computer science, and after postdocs at Carnegie Mellon University and NYU, I joined Northwestern University a few years ago. My research is broadly in theoretical computer science, particularly in designing algorithms and proving guarantees for algorithms. So, I mean, and also in understanding the complexity of various computational tasks, and this is certainly related to one of the top, I mean, the focus of this course. And I do theoretical computer science because I like algorithms. I like mathematically reasoning about them, and I really think that algorithms are a very powerful object which provide a new perspective or lens for all other sciences as well. Okay, so let's move on to this topic. In this topic, we'll be asking some really basic questions about sets. So, given a set, what is the size of the given set? Okay, or given two sets, how do their sizes compare? Is one larger than the other, or smaller than the other, or equal, and so on? Okay, of course, this question is very easy for finite sets. Well, for instance, suppose I give you two sets A, which maybe has some three elements in them, and maybe B, which has two elements in them. I can easily just count the number of elements in these sets. The size of set A is 3, the size of set B is 2, and A has size larger than B. Okay. Well, the main question that we'll try to answer or try to understand in this series of videos is how do we do this for infinite sets? Okay. And there are many infinite sets that I mean you would have encountered before too. For instance, we have natural numbers, which are usually represented by either script n or bold n, or integers, script c, bold c, real numbers, and so on. Okay. Then you could ask these questions. So how do I compare the sizes of these different infinite sets? And apart from these infinite sets, this will also be particularly important in the rest of the course for understanding the power of different model classes, of models and different classes. Okay. Good. So the outline of this topic is going to be split as follows. So the first video is this video, which is the introduction. And the next video is going to be about cardinality of sets. What does it even mean? And how to compare cardinalities using mappings and functions. Okay. The last video it will be on diagonalization, which is a very powerful technique for showing that one set has much larger size than another. Thank you. Hello, everyone. So let's go to the first video on the topic of counting and infinite sets. So in this video, we'll be learning more about what cardinality of sets are, and we'll see how to use mappings to compare cardinality of sets. Okay, so the outline is as follows. We'll first define what cardinality means, and we'll do a quick recap of different properties of mappings. And then we'll see how to use mappings for comparing cardinalities of sets, particularly infinite sets. And then we'll see what countable sets are, and we'll see some examples. Okay, good. Okay, so to recap, the main question we were interested in was how do we compare the sizes of sets? Okay. And if you recall, this was easy for finite sets. Okay, because given a finite set, let's say, yeah, I mean, it has a bunch of elements, you can just count the number of elements. So given any two finite sets, you can just count the number of elements, and then you're just comparing numbers. Okay, but the main question is, how do you do this when you have infinite sets? Okay, and firstly, what do you even mean by a size of an infinite set? And then how do you go about comparing this notion of size? And we will see how to do this using this indirect approach of mappings. But first, when we are talking about infinite sets, we will use this notion of cardinality. Okay, so what is the cardinality of a set? The cardinality of a set is exactly just the size for finite sets, but you can just think of it as a measure of the number of elements in a set. Okay, so you for a given set S, uh, we will use um, this notation, S enclosed within two vertical bars to denote the cardinality. Okay, and this notion is exactly the same. It's equivalent to the size of a set. That is, that's the number of elements inside the set for finite sets. Okay, but we will basically use the term cardinality for infinite sets. Okay, and I'm not, I mean, this is an exact definition, but we will see it. We'll see how to reason about the cardinality of sets using this indirect approach of mappings. Okay, so we'll use cardinality. Okay, good. So before we go into how to do this, let's actually recap what mappings are, and we'll also recap some properties of mappings that will be very useful for us. Okay, so let's recall what a map or a function is. So this figure, we have these two sets, A and B, and we have a map F from A to B. So what is this map from A to B? We call that it's just a way of associating elements of A to elements of B. And if you have a valid map or a function, it maps every element of A to exactly one element of B. What it means is that if you have these lines that indicate which element of A is mapped to which element of B and so on, then it just means that every element of A has exactly one outgoing arc or line. Okay. Now let's look at some properties of maps that we'll be interested in. The first property is what is known as one-to-oneness or injectivity. Okay. So what is injectivity or one-to-one? A map is one-to-one if it never maps, if it does not map two different elements of A to the same element of B. Okay. In other words, if you look at if you look at any of the elements of B, okay, they cannot have, they may have some arcs coming in, but every element of B has at most one arc coming in. So for instance, this vertex, okay, this element of B has two incoming arcs. So this map is not 1, 1. Okay, good. So that's one-to-oneness, or another name is injectivity, and we'll use these interchangeably. The second term is onto maps. Onto, a map is called onto or surjective. Okay, so surjective if it hits every element of P. Okay, more formally, if for every element small v in the set capital V, there exists some element A, okay, such that f of A is equal to B. Okay, so what this means is that every element of V has one incoming arc. So for instance, if you have some element here which has no arc, then this is um, not surjective or onto. Okay, because of it. Good. Now finally, we'll say that a map is bijective, or sometimes this will also be called a correspondence. Okay, it's just a function or a map is called bijective if it is both 1, 1 and surjective, 1, 1 and onto. Okay. So what that means is, in this figure, you'll have exactly, in every element of B has exactly one incoming arc. Okay, not two, not zero. Okay, that's to have exactly one incoming arc. So for a bijective map or a correspondence, you can really just associate every element of B or A to another element of B. Okay, so this figure will look perhaps like this. Okay, so a bijective map gives you a way of associating every element of A is associated with a unique element of B, and vice versa. Okay, so this actually gives you a flavor of why uh, these this notion of maps can be used for comparing sets, because if you can actually establish a bijective map between two sets, then they have the same cardinality. Okay, for finite sets, it's easy to see. If you do have a bijective map, then the two sets should have exactly the same size. Okay, similarly, you can use properties like surjectivity and one-one-ness to also compare the sizes of sets for finite sets. But we will actually use it as a definition for how to compare cardinalities of sets. Okay, so that's what we're going to do next. Okay, now what we're going to do is we're just going to take any two sets. And we're going to see when we can say that the cardinality of one set is less than or equal to the cardinality of another set, or greater than or equal to the cardinality of the other set, or equal. Okay, so we're just going to look at those three cases. Okay, so we have two sets A and B. We'll say that the cardinality of A is greater than or equal to the cardinality of B, okay, if and only if there exists an onto map, surjective or onto map from A to B. Okay, good. So if you can establish, so all you need to do to show that the cardinality of A is greater than or equal to the cardinality of B is to just show the existence of a map. You can design the map that is surjective. You just need to prove that it's surjective, and that will establish that the cardinality of A is greater than or equal to the cardinality of B. Okay, and but this is really a definition. So if there is no such map, then it is the cardinality of A is not greater than the cardinality of B, greater than or equal to the cardinality of B. Good. So similarly, we'll say that the cardinality of A is less than or equal to the cardinality of B if and only if there exists a 1-1, 1-to-1, or I mean, they call this is injectivity, or an injective map from A to B. Okay, so again, to show that the cardinality of A is less than or equal to the cardinality of B, all you need to do is you should define, or you just need to exhibit one map and prove that it is 1-to-1 for inject. And finally, the cardinality of A is equal to the cardinality of B if and only if there exists a bijective map. Okay, so remember that a bijective map is both one-to-one and one-to. Okay, so this is giving you, these are basically definitions of when the cardinality of A is greater than or equal to the cardinality of B, or less than or equal to the cardinality of B, or equal to each other. Okay, and the nice thing is that there's a fact. This definition is consistent with, you know, the same notion for finite sets. So what do I mean by this? So uh, we know that for finite sets, the cardinality of a set is exactly the number of elements in the set. Okay. So given any two sets, you can just count the number of elements in the set and see if it is greater than or less than or equal to each other. Okay. And what this fact is saying is that this definition is consistent with just this notion of the number of elements in the set for finite sets. That is, if you take any two finite sets, A and B, such that A has size greater than or equal to the size of B, then there will exist a surjective map from A to B, and you can exhibit it. Similarly, if the size of A is less than or equal to the size of B, then you can exhibit an injective or a one-to-one map from A to B. And if it's equal, then you can exhibit a bijective. Okay, so the two, this notion of cardinality and uh, really comparing the cardinalities of sets is exactly consistent with what we want for finite sets, but it really extends this notion for infinite sets. Okay, and now I'm just going to state a bunch of uh, theorems or facts about cardinalities and comparisons, and I'll state them really without proof. But the main goal of this is to show that, is to really say that you can use it to reason about sets, the sizes or really how big sets are, just in the same way that you would do with sizes of finite sets. Okay, so here's a theorem, and I'm going to state it without proof. Okay, given any two sets, either the cardinality of A is less than or equal to the cardinality of B, or the cardinality of A is equal to the cardinality of B, or the cardinality of A is greater than or equal to the cardinality of B. Okay. Now, here's another theorem. Okay. If the cardinality of A is at most the cardinality of B, okay, that is, we manage to exhibit a one-to-one map from A to B, and if the cardinality of A is greater than or equal to the cardinality of B, okay, that is, we exhibited a surjective map from A to B, then in fact the cardinality of A is equal to the cardinality of B. That means there actually exists a bijective map from A to B. This is a theorem because, if the cardinality of A is less than or equal to the cardinality of B, it just means that there exists a map which is injective or one-to-one. And similarly, if the cardinality of A is greater than or equal to the cardinality of B, then there exists a map which is surjective. But these two maps need not have been the same. But really, this theorem is saying that, well, there will actually be one map which is both injective and surjective. And so it's a bijective. Okay. Good. So really the main takeaway, well, actually, let me actually maybe give you a little bit of an aside. You can also kind of define, things like what does it mean for the cardinality of A to be strictly less than the cardinality of B. You can say that this is the case if and only if the cardinality of A is less than or equal to the cardinality of B, and the cardinality of A is not equal to the cardinality of B. Okay, and likewise, we can also define the sets, the notion of when B, the cardinality of B is less than the cardinality of A, just in the same way. And really, the two things are the same. And uh, you can talk about when the cardinality of A is less than the cardinality of B, or cardinality of A is greater than the cardinality of B, and or B, cardinality of B less than the cardinality of A, and so on. And really, these are the same things that you can do, the same things that you could do with sizes of sets. And there you're just comparing numbers. And just to say that it's the same, that is, cardinality of A being greater than the cardinality of B is the same as cardinality of B being less than the cardinality of A. Here is a simple proposition. So, yeah. So let F be a map from A to B, that is 1 to 1. Okay, then there exists a map from B to A that is subjective. Okay, it's a very simple proposition, and in fact, I'm going to leave this proof as an exercise. Okay, as a hint, think about these elements in B, and you can try to split the elements in B into two kinds. Okay, those that have those elements in B that have no element in A that is mapped to it. So there is no pre-image for B. And those elements in B which have some pre-image. And then try to think about constructing a map G which maps, which associates, different elements from A to B, depending on whether it's to the first type or the second type. Okay, so this is just a fairly simple proof, so I'll leave it as an exercise. Good. Now let's look at some examples of these infinite sets that we will be, that we would have encountered. For instance, we can take the set of all natural numbers. Okay, usually that is represented by either script n or a bold n. You can have the set of integers or sometimes whole numbers or rational numbers, which we will represent by script q or bold q. Similarly for real numbers and complex numbers. Okay, script r for real numbers and script c for complex numbers. Okay, these are all infinite sets. And now you can ask about, well, how do I compare their cardinalities? Okay, now here's another simple definition that we will use. Okay, And this is specifically with respect to natural numbers. This is, we'll always, I mean, many times we'll be interested in comparing the cardinality of sets, given set compared to the cardinality of natural numbers. Okay, so here's a simple definition. Okay, a set S is countable if and only if it is either finite or the cardinality of S is equal to the cardinality of the natural numbers. Okay, so remember that these are natural numbers. Okay, so for given infinite sets, we would be often interested in whether the set is countable or not. If it's a finite set, it's certainly countable. But there could be infinite sets that are also countable, and you really need to check whether its cardinality is the same as it is for natural numbers. Okay, now here is a simple proposition that is again very easy to prove, and this says that if you have any set, any two sets A and B such that A is a subset of B, then the cardinality of A is less than or equal to the cardinality of B. Okay, again, it's an obvious statement for finite sets, but it's a very useful statement for infinite sets. Okay. So I mean, it's fairly simple still, and the proof is again. Remember what we need to do to show that the cardinality of A is less than or equal to the cardinality of B. Well, we can exhibit a one-to-one map. Okay, as follows. Very simple. So given any for A in capital A, we're just gonna, so this map will be called F. F of A is just gonna be equal to A itself. Now, why is it valid? Well, remember that capital A is a subset of B. So any element small a in capital A is also an element of B. So I can just map A to the same element small a to itself. Okay, and now this is easy to see. That F is a map that is one-to-one. Okay, and this completes the proof. Okay, so now this at once allows you to compare the cardinalities of many of these sets. So this at once implies some simple consequences that the cardinality of natural numbers is certainly less than or equal to the cardinality of rational numbers. Okay, it's also less than or equal to the cardinality of integers, but it's also less than or equal to the cardinality of natural numbers. Rational numbers. It's less than or equal to the cardinality of real numbers. Okay, similarly, the cardinality of rational numbers is less than or equal to the cardinality of real numbers, etc. There are many such simple consequences. Okay, so if one set is a subset of another, then the first set has cardinality that is certainly at most the cardinality of the second set. Okay, But so here's a question. Well, we know that the cardinality of natural numbers is less than or equal to the cardinality of rational numbers. But could the cardinalities be equal? So is the cardinality of rational numbers also less than or equal to the cardinality of natural numbers? Okay. Similarly, is the cardinality of real numbers less than or equal to the cardinality of natural numbers? So really what we are asking is, are rational numbers and real numbers countable sets? Okay. So well, here's an interesting difference between the two, rational numbers and real numbers. As it turns out, and we're not going to see this in this class, the cardinality of rational numbers is exactly the same as the cardinality of natural numbers. Okay, so not only, can you show that it's easy to show that the cardinality of natural numbers is at most the cardinality of rational numbers, but you can also show uh, that the cardinality of rational numbers is at most the cardinality of natural numbers. And you do this by showing a one-to-one map from rational numbers to natural numbers. Okay, so this is countable. So rational numbers is countable. It's a countable set. However, real numbers, it turns out, is uncountable. Okay, so you can actually show that there is no subjective map from natural numbers to uh, real numbers. Okay, and this argument is actually quite involved, and this uses this idea called diagonalization, which we will see in the next lecture. Okay. So just to summarize, we saw what the definition of, we defined what is meant by cardinality of sets, and this is particularly useful. This extends the notion of size to infinite sets, and we saw, maybe recap what mappings are and different properties of mappings, and we saw how to use mappings to reason about cardinalities of sets, particularly how to compare cardinalities of infinite sets. The main takeaway is that you can use cardinality instead of set size to do these kind of comparisons. And many of these comparisons, the same rules that apply for set sizes will also apply for cardinalities. Okay. And yeah, and finally, we saw what countable sets were, and we saw some examples. In particular, we saw that um, rational numbers have the same cardinality as natural numbers. And in the next lecture, we're going to see why real numbers do not have the same cardinality as natural numbers. So real numbers are uncountable. Thank you. Hello everyone, welcome to the video on diagonalization as part of the topic in the theory of computation course on cardinality of sets, infinities, and the diagonalization technique. So just to recap what we have seen in the previous video, we saw what the cardinality of set meant. It's just the size of the set for finite sets, and it extends the notion to infinite sets. And we saw how we could compare cardinalities of sets. In particular, we would say that the cardinality of set A is greater than the cardinality of set B, greater than or equal to the cardinality of set B, if and only if there exists a surjective map that goes from A to B. Okay, similarly, we can say that cardinality of A is less than or equal to the cardinality of B if we exhibit a one-to-one map from A to B. Okay, and this gave us way to compare cardinalities. Then we saw what a countable set was. These were sets that had a cardinality that is at most the cardinality of natural numbers. So any finite set is countable, or if you exhibit a one-to-one map from this set to natural numbers, then it's countable as well. So we saw that I mentioned that rational numbers actually form the set of all rational numbers forms a countable set, but surprisingly, the set of real numbers is an uncountable set. Okay, and to prove this, Cantor came up with this very powerful technique called diagonalization, which will also be very useful in this theory of computing course. Okay, so that's the main thing that we are going to see in today's class. So we'll demonstrate diagonalization, okay, using two different theorems. Okay. First, we will define what the power set of a set is, and then the first theorem will be proving that the cardinality of a set is not equal to the cardinality of its power set. Okay, in particular, it will be strictly less than the cardinality of its power set. And we will use diagonalization to prove this. And finally, we'll actually prove Cantor's theorem, which is that the cardinality of natural numbers is strictly less than the cardinality of real numbers. Okay, and we'll use diagonalization to prove. Good. So before we continue, we'll continue by first defining what a power set of a set is. Okay. Good. So given a set A, the power set P of A is defined to be the set of all subsets of A. Okay. So just for an example, if A is the set 1, 3, and 5, then the power set of A is just going to be the set of all these following subsets. So you always have the empty set. The empty set is always a subset of any set. And then you have the singleton sets here 1, 3, and 5. Then you have these subsets with pairs of elements. And finally, you have the entire set itself. Okay. Good. So this is a power set of A. And so here is a simple fact. For finite sets, then the size of the power set of A is equal to 2 raised to the power of the size of it. Okay. The proof is actually very simple, and you've probably already seen this before, but really the proof is just almost this one line. Basically, we're just counting for a given set A, we're just counting the number of subsets of it. Okay, so here we're just thinking of the size of A as being finite. You can think of it as n, for instance. So this is really just a counting exercise. So to form a subset S of A, okay. So for any element of A, there are really just two choices, okay. Either A is in S or A is not in S, okay. So for the number of subsets that you can have is, for each element you have two choices. So for the first element of A, you have two choices, whether it should be in S or not. Similarly, 2 times 2, and so on. And this is for every element of A, and this is 2 raised to the power of the size of A. Good. Okay. Now, here is the theorem. There is no surjective map F that goes from A to the power set of A. Okay, so really what I'm saying is that there is no map, there exists no map F that goes from A to the power set of A and is surjective. Okay, so just a small note. Okay, it's easy to see that the cardinality of A is certainly less than or equal to the cardinality of the power set of A. Okay, so how do you show this? It's you just construct an injective map. So what this theorem is basically saying is that the cardinality of A is strictly less than the cardinality of the power set of A. Okay, and why is that? It's because the theorem tells you that the cardinality of the power set of A, okay, is not equal to the cardinality of A. But we do know that the cardinality of A is less than or equal to the cardinality of power set of A. So this is the strict inequality, okay, of cardinalities that we have seen in the previous video. Good. So let's do the proof of the theorem. And the proof will actually use, so the proof is actually simple. It's kind of obvious if A is finite. Okay, that's because if it's finite, we know from the fact that the size of the power set of A is actually just 2 to the size of A. And so we know that any number, any natural number n is not equal to 2 to the n. Okay, but really the question is, how do we prove this for infinite sets? Okay, we'll actually prove this by contradiction. Okay, so let's say that F be such a surjection, be a surjective map. Okay, so this is, we're going to then contradict it. Okay, so let's say that it actually exists. Okay, now what we're going to do is we're going to come up with a set. So remember what a surjection means. So we have this map that goes from A to the power set of A, and it means that every element in the power set will have at least one incoming arc. Okay, potentially many, but yeah, so these are good. So what we are going to do is we are going to construct a particular set B which belongs to the power set. Okay, so and this construction of the set will be the key step in the proof. Let B be the set of all elements in A, okay, such that X is not an element of f of x. Okay, so this is a key step. Okay, so the set B will be some set inside the power set. Why is that? Well, will be some element inside the power set. Why is that? Because it's just a subset of elements inside A, and any subset belongs to the power set. And what we are going to do is we're going to this set B is constructed in a special way, and then we're just going to contradict B actually belonging to the power set later. So this will end up showing that there can be no set. Okay. Good. So, and this kind of a step where we are constructing this element of we are assuming a surjective map, and then we are constructing an element in the range. Okay. Uh, and the construction is usually somewhat self-referential. This is a common feature in many of the diagonalization proofs. Okay. So now, just by definition, because it's a subset of elements, B is just a subset of A. Therefore, B is just an element, the power set of A, because the power set contains all subsets. Okay. Okay. Now, since F is a surjective map, there has to exist some Y which is an element of A such that Y, f of Y, is equal to B. So what are we saying? So we are taking this B here. Well, B belongs to the power set, so it has to have at least one incoming arc. And let this element from which this incoming arc came in be Y. Okay, so f of Y is equal to B. Good. Now, just by the definition of B, we have that Y is an element of B if and only if Y is not an element of f of Y. Okay. Right? This is just the definition of B. It contains all elements X such that X is not an element of f of X. Okay, so similarly for Y. Okay, so that is Y is in B if and only if Y is not in B. Okay. Now this is of course this is a contradiction. And this proves that there cannot be any surjective map. Okay, this completes the proof. Okay, so the key step in this diagonalization proof is to construct the set B. Okay, and because there exists a surjection, we looked at this element y that mapped to B, and then the main question he asked us was, well, is y an element of B? Okay, we know that f of y is equal to B. This is because of the surjection. Now we ask, well, is y an element of B? And I mean, then if you go by the definition of B, you see that you reach a contradiction. Okay. So this shows that the size of A, the cardinality of A, that is less than, is not equal. Okay. In particular, it is less than the cardinality of the power set of A. Okay. And we prove this by using diagonalization. Now we will show the second theorem, which will be proven by diagonalization. And this is the theorem of Cantor, famous theorem of Cantor, showed that there is no surjective map from natural numbers script n to real numbers, okay, which we denote by script r. Good. And the proof will be through diagonalization. Okay, so good. So recall that this, by the way, this theorem shows that hence the set of real numbers is not countable. Good. And again, so how do we, so we will show that there is no surjection from natural numbers to real numbers. In fact, we will show something even more particular. We will show that there is no surjective map from natural numbers to just the interval 0 to 1. Okay, remember that the interval 0 to 1 is a subset of real numbers. Okay, and the idea is by diagonalization. And in this proof, after this proof, it will become clear why we actually use the term diagonalization to refer to this technique. So again, let's assume, for sake of contradiction, that there exists a surjection from natural numbers to the interval from 0 to 1. Okay. Okay. So what we will do is we will construct some x, some special real number x, okay, such that there is no pre-image for f, okay, that maps to x. So f inverse of x is really just an empty set. Okay, so there is no element which actually maps to x according to f, and this will contradict the fact that f is a surjection. And we'll actually construct x in stages. Okay. So what do we want to show? We will want to construct this x so that f of I mean, it is, I mean, f of 1 is not equal to x, f of 2 is not equal to x, and similarly, f of no natural number is equal to x. So we'll just do this in stages. So we'll keep ensuring that uh, that all these natural numbers, 1, 2, 3, and so on, cannot be pre-images of x. Okay, so let's actually draw a table which will, indicate this idea more clearly. So let's look at an example. Okay, so maybe we have n, and then you have this surjective map f of n. Okay, and let's look at all the, values that it maps to. Okay, so for instance, 1, let's say it's mapped to some number, let's say 3, 4, 5, 1, and so on. Okay, the number 2 is maybe mapped to 0.87, yeah, 9, 0, 0, 0, so on. Then 3, let's say, is mapped to 0.9, 1, 4, 3, okay, and so on and so forth. Okay, so we will now construct a new, we will construct this number x, and we will construct it in a way that ensures that, f of 1 is not equal to x, f of 2 is not equal to x, and so on. Okay, the way we'll do this is by saying, well, let's consider the ith decimal place of f of I. Okay, so we will choose x so that the ith decimal place of x, okay, differs from the ith decimal place of f of I. Okay, so the ith, right, we'll just write it here, x is chosen such that the ith decimal place of f of I is different from the ith decimal place of x. Okay, so we just keep constructing it, digit by digit. Okay, and in fact, each time we will choose. In the ith step, we will choose the ith decimal place of x, and this ith decimal place of x will only be chosen between, for a reason that I will come to later, will only be chosen between the digits 1, 2, 3 up to 8. Okay, so 0 and 9 are excluded. Okay, and we will choose the ith decimal place of x just so that it is different from the ith decimal place of f of x. So for instance, here, the first decimal place should be different from 3 because that's the first decimal place of f of 1. Similarly, the second decimal place should be different from 7. The third decimal place should be different from 4, and so on. So for instance, I can pick x to be something like 0.46, 5, and so on. Okay, good. Now, so what's the advantage of this construction? By construction, okay, if f of j is equal to x, okay, and if it were a surjective map, then x would have some number j such that f of j is equal to x. Okay, then we see that f of j and x differ in the jth decimal place. This is just by the way we constructed x. Right? For every I, f of I and x differ in the ith decimal place. Okay. So so this yields a contradiction. Because suppose j is a number so that f of j is equal to x. Well, we know that they actually differ in the jth position, so they cannot be the same. Okay. There is one small caveat in this proof, and which is that, in fact, two real numbers, let's say x and y, can be the same even if they differ in their representations. Provided, you know, if you have something of the form, x is just a bunch of digits, okay, followed by 1, 0, 0, 0, 0, 0, 0, so on. Okay, let's say, and y is, you know, the same set of digits, okay, followed by 0 and then followed by 9, 9, 9, 9, 9. Basically, a bunch of trailing nines. Okay, so these two numbers are actually the same, okay, even though they have different representations. But really, in our construction, this cannot happen. Okay, so and the way we ensured this because we picked the digits of x to be only from 1 to 8. Okay, there are enough digits to ensure that from 1 to 8 to ensure that it is not equal to a specified digit. Okay, so we could always just pick these digits from 1 to 8, and in that case, you don't have this issue cropping up. Okay, so this actually completes the Cantor's theorem. Okay, so remember what we did. So we said, well, suppose there was a surjective map from natural numbers to real numbers. Well, we constructed this real number, which is again inside the range. I mean, earlier we picked the set B, which was inside the range. Similarly, here we are going to pick a natural number, which is inside the range. In fact, between 0 and 1. Okay, and we picked it in a very special way. We picked it to ensure that, you know, the ith digit of this number x differs from the ith digit of f of I. Okay, and so really, so this is actually where this diagonalization comes in. The term diagonalization comes in because you see that this really forms a diagonal. Okay, that we are ensuring that these are unequal. And just by construction, you reach a contradiction because if there was a j, a natural number j, such that f of j is equal to x, they both have to differ in the jth bit. And this gives you the contradiction. Good. Now to summarize, in this video, we looked at diagonalization, this technique called diagonalization. We looked at, we first defined what a power set is for a set. And we showed that even for infinite sets, the cardinality of a set is strictly less than the cardinality of the power set. So in particular, the cardinalities are not the same. And we showed this by using diagonalization. Okay. And then we also proved that we proved Cantor's theorem, that says that the cardinality of natural numbers is different from the cardinality of real numbers. And we showed this using diagonalization. Thank you.